Yes, Professor Maeno, we can see the slideshow now. So maybe you can begin with your talk. Can you unmute yourself, please?
Thank you very much for waiting. Okay. Is it okay now? It looks okay.
Yeah, it's okay. It's good. Please.
Yes. Okay. Thank you very much for the introduction, kind introduction, and good afternoon, everybody. And I'm very happy to be an honor to join this very special event. And I'm very happy to see that former postdoc and collaborator, Dr. Chevrel-phaseand, is serving as such an important role in this event. So I'm very happy for you. Okay, so my talk today is on, as the chair introduced, something on a special topic. And then the next speaker, Shingo Yonezawa, will talk about more detailed, more scientific, as basic scientific achievement part of the talk. So my talk is on the periodic table, and let's see how to write. So my name is Yoshiteru Maeno, and this work is in collaboration with another professor who is Koichi Hagino, and we are both in Kyoto University Physics Department, and I'm in experimentalist in low temperature physics, and Hagino is a nuclear theory theorist. And in the introduction, I will talk about the about the Yukawa, just a little bit about Yukawa, and then the Bohr model is the atomic periodic table is the second topic, and then we'll go on to this nuclear periodic table, and then I just combine these two the periodic table at the end. Okay, and then last year was the this international year of the periodic table, celebrating the 150 years anniversary from Mendeleev's periodic law. Okay, so now, so Kyoto University physics has a long tradition of, especially the particle physics, and Yukawa and Tomonaga. Tomonaga got Nobel Prize with Stringer and Feynman. They are actually classmates in our department. And then more recently, Kobayashi and Masukawa received Nobel Prize in physics for their prediction of 3 families of quark. Right? And then to introduce our group, this was group members 6 years ago. Here at the center, you see our chair, Dr. Chevrel-phaseand, and he was the leader of the group working on the this superconducting junctions. He made this single crystal with a film and a device, and he studied exotic properties of superconducting junctions. Okay, and then Mendeleev's table. So 151 years ago, Mendeleev proposed this periodic table based on this periodic law, and this 2 years later he proposed this table 2, which is the known as the ShortForm periodic table. And in here, he classified the elements based on the properties when they are forming some compound, for example, especially oxides and hydrides. And so something forming RO, namely a divalent ion tendency, will be listed here. So in addition to calcium and strontium, also zinc and cadmium are also in the same group. And then, so the representative elements and the transition elements are sort of mixed together, alternating appearance in here. And then, so it has 8 groups. And the modern long-form periodic table this is based on is consistent with the quantum mechanical electronic orbitals, and so it's very reliable. And however, there are some shortcomings. So Mendelev's periodic law is not so explicit here. For example, in Mendeleev table, you can clearly see which element tends to become 2+. Okay. But here, which ones have divergent tendencies? So like this magnesium, calcium, these become 2+. But also here, zinc and cadmium, those tends to become 2+. But it is not so explicitly expressed in this form. So therefore, so before going to this to solve this problem, then do you know who proposed this prototype of this long periodic table? And it's certainly not Mendeleev. Mendeleev proposed this short period table, and with all the rare earth elements separated in a different group. This is his name is not so well known, at least in Japan. This is Alfred Werner, and Alfred Werner is a very well-known, prominent chemist, and he received the Nobel Prize in Chemistry in the same year as a Camariones in Physics Prize. So Camariones received the Physics Nobel Prize in the same year. And he proposed this periodic table as early as 1905. So this is 8 years before Bohr model. Okay, and then he placed these rare earth elements separate from D elements and SPO elements. And S elements are over here, and then P block elements are here. Okay, so Werner's name as an inventor of the modern periodic table is a little recognized. So I really hope that in Pakistan, maybe in education, you make this Werner's name a little more better known. So then to bridge between this short form and long form, or to express a Mendeleev periodic law better based on the long form periodic table, how can we do it? So we could, this is a Janet periodic table, which is similar to Werner's table, but with the S block elements aligned, placed group 1 and 2 placed in this side. And then in this case, you can see the divalent elements appear group 2 here, and then group 12 here, and then there's some tendency at here, the group 32. And then 3+ and 4+ certainly in here, and then in here, group 3 and 4, group 13 and 14. And then also here, the lanthanum tends to be 3+, but the cerium tends to be 4+ in the oxide. So cerium O2 is a stable oxide. So if you look at this, starting from this, how can you recover the expression of the Mendeleev law? And the answer is rearrange the elements in 3-tube helical periodic table. So you form one here, another one here, D block, and then another one with combined P and S. Then you can maybe overlay all the 3+ elements and so on. And that's done in here. So this was my invention about 20 years ago, and this appeared in the cover page of the Journal of Physical Society of Japan. This is like Physics Today in the APS. So JPS, we have this journal, and it covered at the top page. This was 2002, long time ago. Okay, so there have been well-known helical periodic table. Chaltenblant and Janet, the one who invented this, proposed this, the long form periodic table I just showed before. So naturally, he put this 4-tube helicals, S block, P block, D block, and F block. But if you could combine S and P in one tube, then you can recover this Mendeleev's law. So here, it's all the 3+ ions align, 4+ ion align, 2+ ions align, and then this D elements and F elements. So this way it's very continuous, and then also the valence properties are explicitly represented in this kind of table. So this is the element touch. Okay, now then what happens to this? So the periodic table, the elements is this. You have an atom, and then I'll talk about the shell structure of the electrons in an atom. So atom is stable when the electron shells are filled up with electrons, as you know. So in the center we have a nucleus with protons and neutrons, and then the electrons form different orbitals. When s orbitals are filled or p orbitals are filled, you have this helium here and neon here and argon. So those are the noble gas, very stable elements, and with the atomic numbers 2, 10, 18, 36, and so on here. So group 18. So these are chemically inert noble gas, and it used to be called a rare gas, and so on. So this is how we have this modern periodic table. Now, for the Bohr model, so this is the electron states under the Coulomb potential of the nucleus. So the energy is degenerate or split according to this principal quantum number. So, for example, this is just a review of quantum mechanics people learn in undergraduate school. And so with the principal quantum number 1, we have this radial density, the radial wave function times 4 pi r square, has only nodes in only one place at r equals 0. And for quantum number 2, you have a the number of nodes is actually just n. Principal quantum number minus the orbital quantum number. So in this case, L equals 0, so you have two nodes. And here you have L equal 1, so 2 minus 1, so you have only one node. So this node number, n, become more important in the nuclear energy level. So, and then there's a splitting between s and p orbitals. If you look at this, there's s orbitals are more stable. And that's because if you look at this n and p equal 2, for hydrogen level, for the excited states, this 2s and 2p are degenerate because it's given by this energy. However, if you have a multiple number of electrons, then there are interactions, and the main interaction comes in the shielding of the bit of the element, the Coulomb potential. So this s orbitals has a more wave function near the nucleus, so it has a more Coulomb potential. Whereas S2p, the Coulomb potential is shielded by the s electrons, so it has higher energy. So this is the origin of this reversal of 3D and 4s, and that's why we have this periodic table. Now in the nuclear shell model, nucleus is stable when proton orbital shell is filled up with protons, and the magic numbers are this 2, 8, 20, 28, and so on. And those magic numbers are different from the atomic magic numbers. And this shell model was proposed by Meyer and Jensen. And the origin of this nuclear force is proposed by Yukawa. And this is the cartoon. And in fact, this is the atom, first ionization energy, and this is the binding energy of the nucleus in the protons in the nucleus. And in fact, 20, 40, 50, 82. So with those magic numbers, the nucleus is stable. Nuclei are stable. Now, why are there this shell model applicable to nucleus? So for the electrons in the atom, it's clear because you have a Coulomb potential from this core. However, in the nuclei, in the nucleus, there's no additional core at the center. So this is just protons and neutrons moving together. But it's really confined in this the radius of the nucleus, and the Coulomb force, you have this Coulomb energy, and then this can be understood as the exchange of photons between the electrons. And then the protons have this nuclear force we call Yukawa potential. And in addition, we have this very short-range exponential form. And this can be explained by the exchange of pions or Yukawa particles between the nuclei. Okay, and then why then these protons have a similar shell structure? And this is because you can treat this as a mean field. So the protons are confined within this space, and so for a single particle model, you can consider the interaction, this Coulomb, the nuclear force from other nucleons as a mean field. And this mean field is like a harmonic well, so or a square well potential, which confines the proton inside this nucleus. And then another important aspect is that this Coulomb potential is essentially spin independent. So spin dependence appears in a higher order as a higher order effect. But for the nuclear, this single particle model or this nuclear force itself is highly spin dependent. So whether the spins is between the up or up down, the nuclear force is different. Okay, so this become important. So the quantum mechanical, the quantum mechanics lecture, we learned that when you have this harmonic well potential, let's start with the harmonic well, three-dimensional harmonic well potential. Then you have this Hermitian polynomial times Gaussian function. This is and then the energy eigenvalue is just harmonic oscillator. Right. And then if you go to the spherical model, you have a spherical harmonics with the radial wave function, and the radial wave function has this n equal 1 with 1 node, n equal 2 with 2 nodes, and so on. And the different colors specify different overall wave functions. So in three-dimensional case, so you can rotate the particle, just sort of wave function. So this is the energy level. So for the Coulomb potential, this 2s and 2p are degenerate. But here in the harmonic well potential, it's even function and odd function states degenerate each other. So it's a little different degeneracy. So if you look at summarize this, you have this energy harmonic oscillator potential is like this. And then if you make it a little more realistic, you have a Woods-Saxon potential, so that there are some limits in the barrier, and you have this exponential increase in the potential. Right. So in this case, there is some splitting occurs from this space, from this even and odd ones. And for the harmonic well potential, you can identify these magic numbers 2, 8, 20, 40. So it's already different from Coulomb potential because of this even odd degeneracy. And so with Saxon potential, more realistic potential would give further splitting, but still it cannot explain 28. So this number 28 is very important to be explained. And so spin dependence is essential for the nuclear force. So this with the same L, this state splits between the L equals 1/2, minus 1/2, or L plus 1/2. 1/2 is the spin of the proton. So this 4F, in the nuclear scientist term, 1F state splits into this J equals 5/2 and 7/2. And this is the origin of the magic number 28. So that's how this model was successful. But now this Woods-Saxon potential appears in other phenomena. So this is the Woods-Saxon potential. So it's a minus potential, and then it's gradually increasing, exponentially increasing, and saturating. This is actually identical to the Fermi-Dirac distribution function. So it's upside down. So it starts from 1 and goes to 0 at high energy. So this goes from 0 to -1 to 0 at a high distance. So, but the functional form you see is identical, right? So okay. So, and then there is another familiar function recently. So this is we see this very often. So this is the infectious population increasing as a function of time, unfortunately. And then there may be, hopefully, there's a complete saturation, so there will be no more increase in the infectious patients. Right. So this the simplest model for this epidemic is called SI model. It's not so realistic, but the simplest model, susceptible infected model, the simplest epidemic model. So the number of infectious population, the derivative is proportional to n. So this gives exponential increase, right? But then there's a breaking because it doesn't go to infinity because it's limited by the total number of population. So this factor in the exponential, giving exponential will be 1 minus this when the number of infectious people increases, there's some breaking occurring. Okay. So if you just solve this equation, this is very simple, non-linear but very simple differential equations, and the solution is like this. So again, this goes from 0 to 1. So from going from -1 to 0, you need to add 1 to this equation. Then you get this mathematically identical equations. Okay, so this is what I wanted to say. And then, okay, so the chart of the nuclei. So the nuclear scientists use this this map instead of a periodic table. So, but this is Z is the number of protons, N is the number of neutrons. But this is really complete, and but the properties of magic number nuclei are not so clear. So then, are there any periodic table treating the magic number nuclei like noble gases? And interestingly, there was no. And so why not? So we made one, and so this is the nuclear periodic table. So we align based on this level scheme. We put magic number nuclei on this on the right hand side, and then we colored the different orbitals of protons in the nucleus in this way. So this is in some sense a little similar to the atomic periodic table. So this is the nuclear periodic table, and then so to serve this as a periodic table, we have this additional information. So for the maximum deformation is plotted here. So maximum deformation occurs from the spherical nuclei occurs away from the magic number nuclei. So you can see this, and also you can see the unstable nuclei very simply clearly. So this is one, and then we can make it three-dimensional. I hope you can see this. This is a three-dimensional periodic table. You can make it. So so instead of atomic orbitals, you have designated nuclear orbitals. So the magic numbers are aligned on one low: helium, oxygen, calcium. Those are the proton magic number nuclei, and then there's a periodic nature represented here. And the atomic nuclear periodic table here. This is the atomic one. Is the you can compare. And then this has been published. So this is this short. This is an open access articles. So it's I hope if you're interested, please get access to this. Right. So this has been advertised in various media, and this is, for example, online newsletters around the world, many countries. Italy, so it says periodic table that goes straight to the heart, and then Russia and America, and Germany, France and other countries. So we have this paper. To make this paper model, we have something available in our homepage. So if you compare this atomic periodic table to our new nuclear periodic table, you find something interesting. Okay, so the overall alignment is of course different because the potentials are so different. But here for the atomic periodic table, I have a special addition that the magic nuclei are designated in the bold letters here, like a nickel here and then zirconium here. But this tin, lead, fluorodium, these three are actually magic number nuclei. But why do they align here in the atomic periodic table? That's weird, right? So then it turned out that this is because the atomic magic numbers, this xenon, radon, and organescent, okay, these numbers, the difference between these numbers are 32. This is clearly, it's easily understood. This is 2k times 4, where k is 4 is the number of blocks, S, P, D, F. So these are separated between by 32. But somehow the proton magic numbers between these proton magic nuclei are also 32. And this 32 number 32 for the nuclei are really it's a combination of all different orbitals, and it's really fortuitous or accidental coincidence. So, but anyway, because of this, about 2/3 of the alignment of the elements are common between the two tables. For example, if you look at this niobium, tantalum, dubrobium, and this one is also niobium, tantalum, right? And then here, this rare earth and the actinides and lanthanides, lanthanum, cerium up to ytterbium. Here, lanthanum, cerium up to ytterbium, and below that is actinium, thorium, and so on, nobelium. Okay, so these alignments are coincidentally the same. It's just a very interesting thing. So to summarize this, we can compare the atomic periodic table with a new nuclear periodic table that we just invented. And the system is atom and nucleus, and the electrons and protons, and Coulomb potential, and harmonic oscillator of Woods-Saxon potential. And then principal quantum number is a basis for energy level. Here it's a number of nodes in the overall wave function, radial wave function. And then because of a large spin orbit interaction, it has a very special magic numbers. And those are the three-dimensional version. Okay, so then the question is, are there other magic numbers? So there are maybe other systems in which people talk about magic numbers. So maybe we can also visualize these the whole system as a periodic table in the cases where we talk about magic numbers. Okay, so thank you very much. I'm sorry about the technical difficulty of my fault at the beginning, but I wish best wishes for your health and safety. Thank you very much.
Thanks a lot, Professor Maeno. That was indeed a very useful talk on nuclear periodic table, and indeed looking at a periodic table, of another charged particle based on another charged particle, such as proton. So we're now open for questions, and I'd like the audience to please raise your hands or type your questions to send us your questions to Professor Maeno. We'll take a couple of questions only because we're short in time. So I'll allow Arshad Ali to talk. Arshad Ali, can you ask your questions, please?
Can you hear me?
Yeah.
Yes. Okay.
Thank you, Professor Maeno. Great talk. I have a question about the classification of the elements based on geochemistry by Goldschmidt. So apparently the order of all those elements in the periodic table are similar. So if there is any differences or similarities between the Goldschmidt classification and yours, it would be great to share with us. And finally, is it possible to print out this origami style periodic table from your website and have fun with some origami. And thank you very much. Arigatou gozaimashita.
Arigatou gozaimashita. Thank you. So the Goldschmidt classifications, I'm very sorry. It must be, I should have known, but I'm not so familiar with this. So I cannot answer this immediately. Sorry. Yeah. And then for the pattern, yeah, we are just setting this website, so it should be soon available. And then we also have this a fan with this is a nuclear periodic table fan, and this is also available. Okay, I'm sorry not being able to answer the first question. Well, can you rephrase it? Then maybe I can answer.
Professor Maeno, we'll move to the next question for now. Warda with us. Warda, can you ask your question, please? Warda, can you hear us?
Our microphone, okay, now we can.
Warda Mahmoud, can you hear us? Can you please ask your question? Or you can type it maybe. Yes, we can hear you now. Can you please ask your question? There's a bit of disturbance and we don't hear anything. Can you type your question, please? So the question, Professor Maeno, is how the classification of periodic table on the basis of its atomic number?
On the basis of which number?
Atomic number. I mean electron, basically. So which is... So how is the classification of periodic table done based on the atomic number?
The classification of periodic table. So well, of course, the number of electrons are the same as the number of protons. Let me see. So the Coulomb potential given by the number of protons are identical to the number of electrons. So see, I'm not sure if I'm catching your question properly. So atomic periodic table. Yes. So this is essentially given by this the energy scheme under the Coulomb potential with some interaction between the electrons, among the electrons, and this will give you this stable. If the each shells are completely filled, it becomes stable. Am I answering the question? Maybe I should be answering something.
Yes, you are. This is what exactly I was looking for. Dr. Shahbaz would like to ask a question.
Yeah, first of all, thank you very much, Maeno-san, for your very nice talk and also introducing a little bit about me, my work in your group. So my question is about deformation and instabilities. Could we also understand the degree of deformation in this periodic table?
Yes, actually, there are smooth sort of variation. Basically, there are some complications, but the general tendency is that there's a deformation is getting bigger, and then when I circle this blue, it exhibits the maximum. And sometimes there's a small two maximums and so on. And this periodic table is based on the proton magic numbers, and the neutron numbers we choose for each element, the most stable number of neutrons. And this deformation pattern is based on this such a choice of stable, most long life nucleons. So there's a general tendency.
Okay, thank you. Thank you very much.
Thank you, Professor Maeno. We have so many questions, but I can just take another little question, maybe. So I'll ask Khalid Hussain to please ask his question. Khalid Hussain, you're allowed to talk now. Can you ask your question, please?
Did you, sir? Sir, first of all, I'm very thankful that it was so interesting meeting. So simply my question is that to sir, what is major difference between the atomic periodic table and the nuclear periodic table?
Main difference.
It is
Yes.
a main difference, major difference, which can be just concluded by a single word, or we can say that just in one phrase.
So the atomic periodic table is beautiful, as you can see from this color, right? So the alignment is rather regular. But the nuclear periodic table is rather complicated. But to visualize this, you can really recognize this, right? So it's worth recognizing. Just, people just talk about, magic number nuclei. But although this is a rather rough approximation of assigning each orbital, it's not so simple. But to do this, you can really visualize how the magic number shells are made up with other different orbitals. So I think it's sort of capture this complication in the nuclear structure. This is one aspect, yes.
Professor Maeno, another little question. I think I'm trying to take as many questions as possible. So Shaista Taimur asks, can we relate nuclear periodic table with the stability belt? Can we relate the nuclear periodic table with the stability belt?
Stability belt. This you talk about this maybe this chart, nuclear chart. So I'm sorry, maybe I'm not catching this so well. Professor Hagino may be in the audience. Maybe he can.
He's the panelist. He's here. He's among the panelists.
Yeah.
Yes. Hi. Yes. Hello. I'm Hagino. And if this stability belt means the line of stability, I'm not sure whether I can answer this question. But we choose each nucleus, the most stable nucleus for each element. So those elements are along this stability line, stability belt. So I don't think there is a direct connection between the nuclear periodic table and the stability line. So in order to talk about this stability line, perhaps we need to extend this nuclear periodic table by including the number of neutrons.
Yes, how we incorporate the variation of neutron numbers in this table is a challenging question. Yes.
Yeah, it's another future challenge.
Okay, thank you, Professor Maeno. That was a very wonderful talk. We have a lot of questions, but unfortunately we are short on time. And we thank you a lot for sharing with us your discovery of nuclear periodic table.